Imagine holding like a single gram of powder right on the tip of your finger.
Just a tiny speck, really.
Yeah, exactly. It just looks
Yeah.
like ordinary dust, or maybe, a pinch of salt. But if you were to somehow magically unfold all the microscopic, the empty pockets hidden inside that single pinch of powder, like flattening them out completely, it would cover an entire American football field.
Which is just, I mean, it's hard to even visualize that.
It really is. Up to 10,000 square meters of surface area hiding inside something the size of a pea. So today, we are unpacking the science of structured nothingness.
I love that phrase, structured nothingness.
Right. We are looking at what scientists are calling the reticular revolution and our global transition into the decade of MOFs. Our mission in this deep dive into the source material is to really understand the mind-bending physics of materials that are, by volume, mostly just empty space.
And we're going to explore how this structured emptiness is being engineered to solve, well, some of humanity's most existential crises.
Specifically water scarcity and carbon emissions. And for those of you listening and sort of thinking about the future, we are going to outline the massive, completely unexpected career pivot this creates for the 2030s workforce.
Yeah, and it is a remarkable stack of research we have today to go through.
It's a huge stack, yeah.
We are pulling from the official 2025 Nobel Prize in chemistry data, some really cutting-edge academic papers out of MIT and UC Berkeley, highly technical doctoral theses on chemical manufacturing, and even MIT Solve project focusing on sustainable biological housing materials in Kenya.
Okay, so let's unpack this. What exactly is this material, and how is it physically possible for a pinch of powder to hold a football field of empty space? I mean, I feel like if something is mostly hollow, physics would just crush it.
It sounds entirely counterintuitive, yeah, until you look at it at the molecular level. We are talking about the fundamentals of reticular chemistry.
Reticular meaning like a net.
Exactly. Reticular essentially means taking molecular building blocks and linking them together via strong bonds into crystalline, open frameworks.
So it's like a scaffolding.
Think of it as building a microscopic three-dimensional scaffolding. And there are really three main families in this space that we need to understand for this deep dive.
Okay, hit me.
First, we have MOFs, which stands for metal organic frameworks. These use inorganic metals, or clusters of metals, as the joints. And those are connected by organic molecules acting as the struts.
So it's a hybrid structure, like a metal joint, an organic strut, another metal joint.
That is a perfect way to visualize it.
Right.
Then we have COFs, or covalent organic frameworks.
COF, right.
Right. And these are constructed entirely from light elements. Think carbon, hydrogen, nitrogen, oxygen, boron.
So no heavy metals.
Exactly. They are linked by strong covalent bonds without any heavy metal nodes, which makes them incredibly lightweight. And finally, we have MOCOFs.
MOCOF, so mashup of the two.
You guessed it. They're hybrids blending the metal coordination centers of MOFs with the covalent organic frameworks of COFs, basically attempting to get the best properties of both.
Okay, I get the categories, but I'm still stuck on the structural integrity of this scaffolding.
Sure.
Because if we are building a structure that is 90% free void volume, wouldn't atmospheric pressure just instantly crush it like an empty soda can?
You would think so. And honestly, for a long time, the global chemistry community thought the exact same thing.
Oh, really? So this wasn't always a given?
Not at all. Prior to the late 1990s, the overwhelming consensus was that permanently porous coordination solids were essentially impossible.
Huh.
The thermodynamic assumption was that any vacant structure on that microscopic scale would simply collapse in on itself the moment you tried to empty it out.
Just because nature abhors a vacuum? Or just because the walls are too thin to support the weight?
Both, essentially. And the historical timeline leading to the 2025 Nobel Prize illustrates this perfectly. If we go back to 1989,
Okay.
a pioneer named Richard Robson at the University of Melbourne created these early, highly unstable coordination polymers.
Unstable being the key word there, I'm guessing.
Very unstable. He linked positively charged copper ions with these four-armed organic molecules, and under an electron microscope, it looked like a beautiful diamond lattice full of cavities.
Wow.
It was a huge conceptual breakthrough.
But I'm guessing it didn't hold up in the real world.
It fell apart almost immediately. The moment you remove the liquid solvent from the pores or expose the structure to even mild capillary forces, the entire thing collapsed.
Ah, so you can build it, but you can't use it.
Right. It was like trying to build a skyscraper out of wet spaghetti. You can link it all together while it's submerged in water, but the second you take the water away,
The spaghetti just slumps. It can't hold its own weight.
Exactly.
So how do we get from wet spaghetti to the rigid molecular parking garages we have today? Because clearly we figured it out.
We did. The first major leap came in 1997. Susumu Kitagawa at Kyoto University proved that permanent porosity in these spaces was
Hmm.
actually a physical reality. He created the first porous coordination polymer that could reversibly absorb and release gas molecules like nitrogen and oxygen without falling apart.
Did he use a stronger metal than copper? Like, how did he fix the spaghetti problem?
It was actually less about the metal and more about the nature of the framework itself. He utilized flexible linkers, creating what they called pliant or breathing frameworks.
Breathing frameworks.
Yeah. Instead of trying to build a perfectly rigid wall that might shatter, he built a structure that could dynamically adapt and change its pore dimensions when guest molecules entered or left.
Oh, that's wild.
Think of it more like a microscopic lung than a rigid building.
Okay, a lung is amazing for breathing, obviously, but if we want to build a trap that specifically filters carbon or water out of the air, don't we need a rigid building?
Yes.
Because if the walls are constantly flexing and breathing, it seems like it would be really hard to control exactly what size molecule fits inside, you know?
That is a brilliant observation, and it brings us right to the breakthrough that earned Omar Yagi his share of the 2025 Nobel Prize.
Okay, let's talk about Yagi.
Yagi realized that using single metal ions as the cornerstones of the framework, like Robson did with copper, resulted in weak, flimsy joints.
Right, because it's just one atom.
Exactly. A single atom acts like a ball and socket joint. The struts attached to it can twist, shear, and eventually collapse under strain. So in 1999, Yagi introduced a game-changing concept called secondary building units, or SBUs.
Secondary building units. Okay, break that down for me. What does that actually look like in our microscopic skyscraper analogy?
Instead of a single metal atom acting as a joint, an SBU is a rigid, highly connected, inorganic metal oxide cluster.
And the cluster.
Yes. Imagine a solid cluster of zirconium and oxygen atoms locked together in a very specific geometric shape, like a microscopic, multi-sided block.
Ah, okay. So instead of a single fragile pivot point, you have a solid three-dimensional anchor.
Precisely. These clusters act as exceptionally strong, rigid architectural cornerstones. When you connect these robust metal oxide clusters with charged organic linkers, you form incredibly strong, highly directional coordination bonds.
Meaning they don't wiggle around.
Right, because the SBU block has a specific geometry. The struts can only attach at very specific angles, and they literally cannot twist. Yagi used this to create MOF5, which is a foundational material in reticular chemistry.
And it didn't collapse.
Not at all. Even when completely emptied of all guest molecules, MOF5 can be heated to 300 degrees Celsius without the scaffolding collapsing.
That is incredible. The empty space is structurally locked in.
And this really ushered in the era of rational design. Because the SBUs are so stable, chemists don't just mix things and hope for the best anymore.
They can actually engineer it.
Exactly. They can predetermine the target topology, they can customize the length of the organic struts, or change the chemical properties of the internal walls without the underlying building collapsing.
Which means you are literally designing a customized atomic scale trap. And this is where I want to pause and zoom out for a second for you listening. We aren't just discussing abstract laboratory theory here.
No, not at all.
These customizable molecular traps are going to be in our homes, our factories, and our supply chains within the next 10 years. We are talking about materials that are fundamentally altering how we interact with the atmosphere itself.
It's a total paradigm shift.
So what can we actually do with these microscopic parking garages?
The most profound humanitarian application currently deploying is atmospheric water harvesting. And looking at the sources, this ties directly back to Omar Yagi's personal history, which heavily influenced the direction of this entire scientific field.
Yeah, the sources spend a lot of time on his background, and it is fascinating. He was born into a Palestinian refugee family in Amman, Jordan.
Right.
And anyone familiar with the Middle East knows that is an incredibly water-scarce region. He immigrated to the United States alone at the age of 15, barely speaking English, and navigated the public education system.
Yeah, he started at Hudson Valley Community College.
Which is just awesome, and then transferred to SUNY Albany for his chemistry degree.
And Yagi credits that specific background, growing up in a desert environment where water was a precious, heavily rationed commodity, as the core drive for his research into water capture.
He wanted to pull water out of thin air.
He wanted to look at the sky and conjure drinking water directly from desert air.
Which sounds like magic or science fiction, But the sources highlight a specific framework his team built called MOF 303. But I need to understand the mechanism here. I mean, I have a sponge in my kitchen, right? It absorbs water. How is a microscopic metal framework different from just a really good kitchen sponge?
To understand MOF 303, we have to look at the exact architecture of its pores. It is a robust aluminum-based framework.
Okay, aluminum.
But the magic lies in how the interior walls of the pores are decorated. The framework is lined with alternating hydrophilic, which means water-loving, and hydrophobic, which means water-repelling pockets.
Hey, hold on. Why would you want water-repelling pockets in a machine designed to catch water? Wouldn't you just want the whole thing to be water-loving?
That is a very common misconception, actually. If the entire pore is hydrophilic, it grabs the water molecules and refuses to let them go.
Oh, hold on too tight.
Exactly. You would have to heat the material to extreme energy-intensive temperatures just to boil the water back out. By alternating the pockets, you control exactly how the water behaves inside the trap.
Okay, walk me through the sequence. A molecule of water floats into this microscopic aluminum cave. What happens?
The hydrophilic pockets act as strong initial adsorption sites. Because of their chemical makeup, they form strong hydrogen bonds with the incoming water vapor.
Okay.
They seed the very first water molecules from the air, locking them into place.
Like little anchors.
Right. And once those initial anchor molecules are stuck to the wall, additional water molecules from the air start to bond to those anchor molecules rather than the wall itself.
So the water starts grabbing other water?
Yes. They form isolated clusters, which then grow into long chains and finally form a complete three-dimensional water network filling the entire void of the pore. But because they are positioned next to those hydrophobic water-repelling pockets, the massive cluster of water isn't glued entirely to the walls.
Which means it's easy to get out.
Exactly.
You just need a tiny push to release the whole cluster.
Exactly the point. Because of this alternating design, MOF 303 can pull water from the air at just 10 to 20% relative humidity.
That's insanely dry.
To give you context, 10% humidity is the hyper-arid Mojave Desert.
But it's not just the sheer capacity in dry air that makes this revolutionary, right? The sources mention a massive flaw with older atmospheric water generators, something about the speed of the cycle.
Yeah, so older water harvesters relied on traditional sorbents like silica gels or zeolites.
Like those little packets you get in a shoebox.
Exactly. And they were typically designed to perform one single water harvesting cycle per day. The material would sit out all night absorbing moisture from the cool air and then release it all day when the hot sun heated the device.
Right.
But if you only cycle once every 24 hours, your total water output is severely capped.
Because once the sponge is full, it's full, and you have to wait for the sun to bake it out.
MOF 303 exhibits what we call rapid cycling. Because those water clusters are so perfectly structured and easily released, it doesn't take hours to fill up and empty out.
Oh, so it's faster.
Much faster. It can perform an entire absorption and desorption cycle within minutes under a very mild temperature swing.
So instead of filling up once a night, it's filling up and emptying dozens of times a day.
Yes. And the data is staggering. A device equipped with MOF 303 can generate 1.3 liters of water per kilogram of MOF every single day in an indoor environment at 32% humidity.
Wow.
And even in the extreme conditions of the Mojave Desert at 10% humidity, it generates 0.7 liters per kilogram of MOF per day. We're looking at a full order of magnitude improvement over anything previously built.
Okay, here is where my layman's logic kicks in.
Let's hear it.
If MOF 303 is so amazing and it catches water so well, why not just make the molecular struts longer? I mean, if we make the room bigger, we can catch more water per cycle, right?
That is the most logical next step. But chemically, it is a nightmare.
Oh, really?
Yeah, this is the classic conundrum of reticular chemistry. If you expand the pore, using traditional methods like just throwing in larger aromatic carbon rings to act as longer struts, the framework usually becomes too hydrophobic, meaning it won't seed the water anymore. Or worse, it loses its rigid geometry and simply falls apart when exposed to moisture.
Because the longer the strut, the weaker the middle gets, just like real architecture.
Exactly. But the chemists found a workaround. The sources detail a specific strategy called the long arm linker extension.
The long arm. Okay.
Instead of redesigning the whole strut, they created a new framework called MOFLA2-1. They took the original organic linker and carefully appended a single vinyl or furan group to it.
Okay, what does adding a vinyl group actually do physically?
It acts like an elbow
I
extension.
mean, elbow extension.
Yeah. It literally gives the molecule a longer arm to hold the massive metal nose just slightly further apart while perfectly preserving the exact chemical alignment of those alternating hydrophilic and hydrophobic pockets.
So it makes the room bigger without messing up the walls.
Right. The resulting architecture increased the total pore volume significantly without compromising stability. This single structural tweak resulted in a 50% increase in water capacity compared to the state-of-the-art MOF 303.
A 50% jump just by extending the elbow. That is incredible, but the sources mention another material that pushes this even further into the realm of the absurd.
Oh, McGallet.
Yes,
Yeah.
McGallat. The data here says it harvests water at 0.2% relative humidity. I don't even know how to visualize 0.2% humidity. That is functionally zero. How can a material pull water out of bone-dry air?
McGallet is synthesized from low-cost gallic acid and magnesium. It is working at the absolute sheer thermodynamic limits of humidity detectability.
Just insane.
To understand how it works, we have to talk about the physics of hydrogen bonding. The framework channels of McGallet contain extremely dense concentrations of oxygen-containing groups.
And oxygen loves to bond with hydrogen, which is the H in H2O.
Yes, but it's not just a casual attraction. At the quantum and molecular level, the electromagnetic pull exerted by these specific oxygen groups inside this ultramicroporous channel is so immense that if even a single rogue water molecule happens to drift past the pore,
Just wandering by.
exactly, the electrostatic force overcomes the ambient thermal energy of the dry air and violently snaps the water molecule into the framework. It is the ultimate molecular trap.
Wow. Okay, so we've established that MOS are the undisputed champions of catching water. But this brings me to a massive contradiction that I noticed while reading the sources.
Okay.
Water is fantastic if you are dying of thirst in the desert, but another huge application for these materials is industrial gas capture, specifically pulling carbon dioxide out of factory smokestacks. Now, I know from reading about traditional carbon capture that moisture is usually the enemy. Traditional amine scrubbing is highly corrosive, takes a ton of energy, and if the smokestack gas is full of steam, it ruins the process.
That is exactly the carbon capture paradox.
Right. If MOFs are so aggressively good at grabbing water, wouldn't a humid factory smokestack just instantly clog the pores of the MOF with steam, leaving no room for the CO2?
In almost all traditional porous materials, that is exactly what happens. Water easily outcompetes CO2 for binding sites.
So it's a huge problem.
It is, but this is where the surgical precision of reticular chemistry comes into play. The researchers tackle this not by blocking the water, but by changing the rules of the game inside the pore.
Okay, I'm listening.
The sources highlight a specific zirconium-based framework called MOF 808.
So they changed the metal node to zirconium?
Yes, but the real magic is the modification. They subjected MOF 808 to something called post-synthetic functionalization.
Post-synthetic functionalization. Try saying that 3 times fast.
Right. It just means after they built the scaffolding, they went back in and chemically glued specific molecules to the interior walls of the empty space.
Like painting the walls of the room.
Essentially, yeah. And in this case, they used amino acids, specifically glycine or D-lysine.
Amino acids, like the building blocks of the proteins in our bodies.
Yes. They covalently anchored the dangling amine residues of these amino acids directly to the zirconium nodes. This fundamentally altered the chemical environment of the empty space. It created a highly basic or alkaline environment inside the pore.
Okay, so the inside of the pore is now highly alkaline. How does that solve the steam problem?
It turns a bug into a feature.
How so?
When the factory flue gas enters the MOF, it is full of both CO2 and ambient water vapor. But because of that highly basic amino acid environment, a chemical reaction is triggered. The captured CO2 actively reacts with the ambient water right there inside the pore to form an entirely new molecule,
Wait,
bicarbonate.
it uses the annoying water vapor as an ingredient to chemically convert the CO2 into bicarbonate?
Yes, it doesn't just trap the CO2 gas, it forces it to combine with the water. And this is a massive revolution for the energy economics of global carbon capture.
Why does converting it into bicarbonate make it cheaper to operate?
Because of how you get it back out. In traditional carbon capture, the CO2 bonds so strongly to the filter that you incur a massive energy penalty.
Meaning you have to use a lot of power to clean the filter?
Right. You have to blast the filter with extreme thermal heat to break the bond and release the CO2 so you can pump it underground. Heating massive industrial columns takes an exorbitant amount of electricity or fuel.
But because it's bicarbonate,
Because it's bicarbonate, the bond dynamics are completely different. The sorbent can be regenerated using mild vacuum swing adsorption.
So no heat.
You don't need to blast it with heat at all. You simply drop the ambient pressure. Under a vacuum, the bicarbonate breaks back down, releases the pure CO2 gas for storage, and the MOF 808 is instantly ready for the next cycle.
That is wild.
In simulated cold flue gas tests, they ran this material through at least 80 continuous cycles with zero degradation in its working capacity.
That is a staggering improvement in efficiency. And looking at the stack of papers, the innovation in gas separation is moving in multiple directions simultaneously. The sources mention another framework, COF 999, which is a covalent organic framework specifically optimized for direct air capture, or DAC.
Right, direct air capture.
So that's literally just sucking ambient CO2 out of the normal atmosphere, not just concentrated factory smoke. But I want to ask about how we actually power these reactions. Because dropping pressure requires massive mechanical vacuum pumps, right?
It does.
Is there a way to trigger these materials at a subatomic level, say by just running an electrical current through them?
That is an incredibly active area of research. Professor Mircea Dinka's lab at MIT is exploring exactly this with a process called electrochemically mediated carbon capture, or EMCC.
Running electricity through the filter to make it grab carbon.
Yes. They are using non-aqueous sorbents called N-heterocyclic amines. This allows the capture and release process to be driven entirely by electron transfer, meaning you can plug the system directly into a solar panel or wind turbine.
But wait, if it were that easy to just zap it with electricity, wouldn't we have done that already?
We tried, but older electrochemical systems ran into a fatal flaw called parasitic oxygen reduction.
Parasitic oxygen reduction? That sounds awful. Can you translate that into something I can visualize?
Think of it this way. You are trying to feed electrons to your carbon capture molecule so it has the energy to grab CO2.
Okay.
But the ambient air is full of oxygen, and oxygen is an absolute glutton for electrons. In older systems, the moment you ran a current through the liquid, the oxygen molecules would swoop in and steal the electrons before the carbon capture molecules could use them.
Oh, wow.
It acts like a parasite stealing the host's food. The oxygen reduction reaction wastes all your electricity and creates corrosive byproducts.
So how did the MIT lab fix the parasite problem?
By designing highly specific N-heterocyclic enamine molecules that are electrochemically tuned to essentially ignore the oxygen.
They just bypass it entirely.
Yeah, they can transfer electrons at a voltage where oxygen doesn't interfere, completely avoiding the parasitic side reactions.
And speaking of running electricity through MOFs, the sources brought up John S. Anderson's lab at the University of Chicago, which seems to be breaking the fundamental rules of these materials.
Oh, definitely.
Because from what I understand, a metal organic framework is basically a plastic strut connecting a metal joint. Plastics are insulators. MOFs shouldn't be able to conduct electricity, right?
Traditionally, no. MOFs are fantastic electrical insulators. But Anderson's lab is synthesizing highly conductive MOFs by altering the electron pathways along the organic struts.
So they changed the wiring.
Basically.
Yeah.
They're creating solids that can be easily fabricated and molded like plastics, but conduct electricity like metals. They provide massive, rapid ion channels that could charge solid-state batteries incredibly fast.
The sources also mention his lab is building magnetic MOFs. I assumed this was to pull heavy metals out of water or something, but the paper says they are using magnets to separate oxygen from the air.
Yes.
How does a magnet grab oxygen isn't a metal?
It comes down to quantum mechanics and a property called paramagnetism.
Paramagnetism.
While oxygen isn't a chunk of iron, molecular oxygen, O2, has two unpaired electrons in its outer orbital shell. Because electrons have a property called spin, these unpaired electrons act like infinitesimally small magnets.
Wait, the air we breathe is slightly magnetic?
Yes, it is a paramagnetic molecule. It is weakly attracted to magnetic fields. Anderson's lab recognized this and engineered a porous MOF with magnetically active metal nodes.
So they put magnets in the joints.
Exactly. When air flows through this framework, the magnetic nodes selectively grab the paramagnetic oxygen molecules while letting the non-magnetic nitrogen pass right through.
Why is that a big deal industrially? Because, I mean, it sounds cool, but what's the practical application?
Because of how we currently separate oxygen, hospitals, steel mills, and chemical plants need thousands of tons of pure oxygen. Right now, the only way to get it is through massive, hugely expensive cryogenic cooling.
We freeze it.
We literally have to freeze the air until it turns into a liquid to separate it out. Bypassing that cryogenic step and separating oxygen at room temperature with magnets would wipe out billions of dollars in electricity costs globally.
Okay, this all sounds like a utopia of material science. Powders that pull water from the desert, turn CO2 into bicarbonate, and separate oxygen with magnets.
It's pretty amazing.
But as I read through the engineering theses in our source pile, I hit a massive wall of reality.
Ah, yes, the scale-up problem.
Right, because synthesizing a few milligrams of perfect, pristine powder in a controlled university laboratory is one thing. If you want to build an industrial-scale carbon capture device or a water harvester for a village in Chad, you have to build macro devices. And if you just take a giant metal column and pack it full of this ultra-fine MOF powder, it's going to pack down like baking flour. It would become a dense brick and completely block all the airflow.
This is the absolute critical engineering bottleneck of the reticular revolution, the transition from powder to macro device. And the problem actually starts before you even try to pack it into a column.
It does.
Yeah, it starts with the fundamental problem of how you dry the framework after you synthesize it.
Dry it like in an oven.
If you put it in an oven, you destroy it.
Oh.
When you synthesize an MOF or a COF in a vat, it initially forms as a wet gel. All of those microscopic football field-sized pores are completely flooded with liquid solvent used to create them.
Right, it's wet.
If you try to dry that gel using normal thermal evaporation like baking it, you run into the nightmare of capillary forces.
Let's visualize capillary forces. Is that the same physical force that pulls water up the fibers of a paper towel?
Yes, capillary action is driven by surface tension. As the liquid solvent evaporates from the pore, the surface of the liquid recedes. But because the liquid wants to cling to the walls, it forms a meniscus, a curved surface, like a U shape.
I remember seeing that in chemistry class, test cubes. The water clings to the glass sides.
Now imagine that U shape inside a delicate microscopic organic scaffolding. As the liquid evaporates and the meniscus shrinks, the surface tension acts like a microscopic vice.
Oh, wow.
It exerts an incredible, violent mechanical stress on the delicate walls of the framework. It literally pulls the walls inward until the pores crush themselves.
Which instantly ruins the thousands of square meters of surface area we just spent all this time engineering.
Exactly.
So if we can't bake it and we can't just let it evaporate, how do we get the liquid out without crushing the building?
The gold standard solution detailed in the engineering sources is supercritical carbon dioxide drawing, often written as CCO2.
Hold on, isn't it wildly ironic to use carbon dioxide to dry a material that's specifically designed to capture carbon dioxide?
It is wonderfully ironic, but it works flawlessly because we are manipulating the phases of matter. We aren't capturing the CO2 here, we are using it temporarily as a high-pressure processing fluid.
Okay, walk me through the exact steps.
You take the wet MOF gel, and you exchange its liquid solvent with liquid CO2 under high pressure.
Okay.
Once the pores are full of liquid CO2, you seal the chamber and raise the temperature past 31 degrees Celsius, and you raise the pressure past 74 bar.
That sounds intense.
It is. At this precise thermodynamic threshold, the carbon dioxide passes its critical point and becomes a supercritical fluid.
A supercritical fluid? I've heard the term, but I don't intuitively grasp it. It's not a gas, and it's not a liquid.
It is a bizarre hybrid state. It has the density of a liquid, meaning it can dissolve things, but it expands to fill a container like a gas.
Why does that help us save the microscopic scaffolding?
Because it is no longer a true liquid,
Mm-hmm.
a supercritical fluid has absolutely zero surface tension. There is no meniscus. Imagine trying to drain a massive, delicate, above-ground swimming pool that is supported entirely by the outward pressure of the water inside it.
Okay.
If you pump the liquid water out, the thin walls immediately buckle and collapse.
Right.
Using supercritical CO2 is like instantly, magically turning all the water in that pool into a thick, dense fog, and then just opening a window and letting the fog gently blow away on the breeze. The walls never feel the pull of the water leaving.
That is a phenomenal metaphor. The fog just drifts out of the microscopic pores, leaving the structure totally intact.
Yes. You slowly vent the supercritical CO2 out of the chamber, the pressure drops, and the framework is left perfectly, immaculately dry, with its delicate architecture entirely undisturbed.
And the data supports this.
Oh, absolutely.
Yeah.
Studies in the source material show this specific drying technique can increase the accessible surface area by up to 1,200% compared to normal thermal drying.
Okay, so we have successfully dried the powder without crushing it, but we still have the original problem. It's still a powder. It's still going to pack down like flour if we put it in a machine. How do we form it into a usable, breathable shape?
The sources point to a few incredible macroengineering techniques. One is called in situ growth.
In situ,
Yeah,
like in place.
exactly. Rather than synthesizing a vat of powder and trying to glue it to a surface later, you crystallize the MOF framework directly onto the target material during the chemical reaction.
Like growing crystals on a rock in a kid's science kit.
Very similar. It's exactly like growing rock candy on a string. You take a highly porous substrate, like an aluminum metal foam, or a ceramic honeycomb structure similar to a catalytic converter,
Right.
and you submerge it in the chemical precursor bath. As the MOF crystals form, they nucleate and grow directly onto the solid struts of the foam. This creates a permanent, highly porous, breathable coating that won't pack down or blow away.
That makes perfect sense for a rigid filter. But the sources also discuss flexible materials. There is a whole section on Professor Zachary Smith's lab at MIT creating mixed matrix membranes, or MEMs.
Yes, the MAM.
They want to use MOFs for large-scale industrial gas filtration, like wrapping a smokestack, but MOF crystals are brittle. So they disperse the water-stable MOF nanoparticles into high molecular weight polymer plastics.
It is a brilliant concept. You take the immense filtering power of a MOF and embed it in the flexibility of a cheap industrial plastic.
Like mixing chocolate chips into cookie dough. But the thesis notes a huge problem with this approach, something they call the interfacial defect.
Yes, and the chocolate chip metaphor actually helps explain the defect perfectly.
Oh, okay, lay it on me.
The organic plastic polymer and the inorganic rigid MOF crystals do not naturally want to stick together. When you mix them and the plastic dries, the polymer chains pull away slightly from the rigid MOF crystal.
Oh.
This creates microscopic voids, empty spaces, right at the boundary interface between the crystal and the plastic.
So the dough pulls away from the chip, leaving a tiny air pocket. Why is that bad?
In a filtration membrane, gas will always take the path of least resistance. If you have a highly restrictive MOF pore designed to catch CO2, but right next to it is a comparatively massive empty void caused by the plastic pulling away.
The gas just goes around it.
Exactly. The gas will just flow right through the empty void, completely bypassing the MOF. It totally ruins the selectivity of the membrane.
So how did the Smith lab fix the defect? How do you make the dough stick to the chip?
They solved it through a highly targeted post-synthetic modification. Before mixing the MOS nanoparticles into the plastic, they chemically modified the outer surface of the crystals. They grafted oligomeric imide chains onto the exterior of the MOF.
Oligomeric imide chains. Please translate that for me.
Crucially, these specific chemical chains are structurally identical to the surrounding plastic matrix, specifically a commercial polymer called 6-FDA-derene.
Ah, I see. They essentially dressed the rigid MOF crystals in a fuzzy coat made of the exact same material as the surrounding plastic.
That is exactly right, because the surface of the MOF now chemically matches the plastic matrix. They blend perfectly and seamlessly. There is no repulsion.
So no empty pockets.
Right. The polymer chains entangle with the grafted coat, eliminating those microscopic voids entirely.
Ah, that is incredibly clever.
And the performance data proves it. Because of this homogeneous dispersion, they were able to load the plastic with up to 40% MOF crystals by weight without making it brittle.
Wow, 40%.
This resulted in a 48% increase in CO2 permeability compared to just using the plastic alone. Furthermore, it remains physically stable over time because the rigid MOF anchors prevent the flexible polymer chains from aging, sagging, or warping under pressure.
All of this engineering is brilliant, but there is still the ultimate question of scale.
Scale is always the hardest part.
Making a perfect piece of plastic in an MIT lab is one thing. But synthesizing MOFs is historically slow. The sources state that the traditional way to cook a batch of zirconium MOFs takes 48 hours of slow cooking in a massive heated vat of toxic solvents. If we are going to deploy thousands of tons of this material globally, we need a better way.
And this brings us to a thesis by Sujay Baji at MIT on continuous flow synthesis.
Yes, this part was fascinating.
This is where advanced chemical engineering meets mass production. Moving from a batch reactor to a continuous flow reactor changes the entire economic equation.
What is the fundamental difference between batch and flow for those of us who aren't chemical engineers?
A batch reactor is like making soup in a massive pot. You put all the ingredients in, heat it up, wait 2 days, empty the pot, clean it, and start over.
Sounds tedious.
It is inherently slow and wastes a lot of energy heating and cooling the massive vessel. A continuous flow reactor, on the other hand, is like a highly pressurized pipe. You continuously pump the chemical precursors into one end of the heated pipe, The reaction happens as the liquid travels down the length of the tube, and the finished MOF crystals continuously pour out the other end.
It's an assembly line for molecules.
Exactly. Bege's thesis demonstrated that by optimizing the thermodynamics, specifically running the flow reaction at 150 degrees Celsius under intense pressure, they forced the MOF to crystallize incredibly fast.
How fast?
They reduced the required crystallization time from 48 hours in a batch pot to just 5 minutes in a continuous flow tube.
5 minutes. That is a monumental shift.
It gets better. Because the flow environment is so highly controlled, they drop the required solvent volume by 84%.
So less waste.
This reduces toxic waste and increases the overall productivity of the manufacturing line by 2 full orders of magnitude.
And this is exactly what allows massive chemical conglomerates like BASF to finally commercialize MOFs and produce them on a truly industrial scale for global deployment.
Without continuous flow synthesis, the decade of MOFs would remain a laboratory curiosity.
Which brings us to the most practical, actionable part of this deep dive for you, the listener. If chemical companies are aggressively scaling up production using continuous flow, and we are going to deploy these massive reticular systems across the globe in the 2030s for atmospheric water harvesting and carbon capture.
Someone has to actually do it.
Exactly. Who is actually going to do the physical work? What does the career pivot look like for the everyday professional?
The deployment of these materials is going to require a massive, entirely new workforce. And it represents a profound shift in global logistics.
Yeah.
For the last century, our supply chains and workforce have been built around extracting, shipping, and burning dense, heavy, robust materials: coal, oil, steel, grain.
Things you can just dump in a truck.
Exactly.
Yeah.
We are now transitioning to a world that must synthesize, deploy, and maintain highly sensitive, microscopically structured materials.
The sources are explicitly clear on the opportunity here. If you are listening and you have existing expertise in material handling, supply chain logistics, quality assurance, or industrial plant operations, your practical skills are about to be in incredibly high demand.
But the operational stakes are fundamentally different. You aren't shipping a train car full of gravel anymore. You will be managing the high-stakes logistics of transporting extraordinarily fragile, highly tuned powders, aerogels, and mixed matrix membranes to remote, hostile environments.
Right. Imagine the logistics of deploying Yagi's water harvesters to a remote, sun-baked village in Chad, or transporting MOF 808 carbon capture membranes to a retrofitted, vibrating coal plant in Texas.
You have to ensure these materials arrive completely undamaged. If a shipping container gets too hot or is exposed to the wrong chemical vapor in transit, or if a forklift operator drops a pallet and exerts massive mechanical shock, you could fracture the macroscopic structure or contaminate the pores, rendering a $1 million atmospheric filter entirely useless. We need logistics professionals who understand how to handle life-sustaining atomic-scale technologies at a macro level.
And reading through the sources, it seems this new workforce won't just be operating blindly. They will be heavily augmented by artificial intelligence.
Oh, heavily.
I mean, the sheer number of possible MOF structures you can build by combining different metals and organic struts is practically infinite. Right?
It is chemically limitless.
Yeah.
And to find the perfect molecular trap for a very specific industrial exhaust gas, we don't have the time or money to manually synthesize and test millions of variations in a physical lab.
It would take centuries.
The sources reference computational research at Argonne National Laboratory. They're using supercomputers coupled with generative AI models to virtually screen over 120,000 hypothetical MOF candidates in just 30 minutes.
30 minutes? That's just insane.
The AI simulates the thermodynamic properties of every single structural combination, identifying the exact top-performing candidates before a human chemist ever steps into the physical lab to synthesize them.
We are also seeing this future workforce integrate heavily into the concept of the industrial circular economy. I found this part of the reading incredibly compelling.
It's so important.
The curriculum from CM Tech highlights that we shouldn't be resorting to destructive mining of pristine new metals to build these billions of microscopic nodes.
The circular economy dictates that the precursors for these frameworks must be sourced from existing waste streams.
Like what?
Well, the curriculum gives a striking example. Extracting aluminum from toxic acid mine drainage, which is a severe environmental hazard, and using that recovered aluminum as the fundamental metal nodes to synthesize MOF 303.
Let that sink in. You are literally taking an active environmental hazard, a toxic sludge ruining local watersheds, recovering the metal from it, and upcycling it into a machine that pulls pure drinking water directly from the desert sky.
It's incredible.
It is the ultimate manifestation of circular engineering.
And to really solidify this concept of circular, structured materials, our sources included a fascinating parallel technology.
Yeah, I wanted to get to this.
We have spent this entire time dissecting synthetic, human-engineered reticular frameworks. But nature has been building structured, porous, functional networks for hundreds of millions of years.
Yes, the MIT Solve project featuring mycoboards. I thought it was strange to include biological housing materials in a stack of chemistry papers, but it perfectly parallels everything we're talking about.
It really does.
This project is driven by a company called Inua Mycotile, operating in Kenya. They are tackling two massive systemic problems simultaneously: agricultural waste and a severe lack of affordable, sustainable housing.
In many regions that grow wheat and rice, farmers are left with massive amounts of leftover stalks and straws after the harvest. Historically, they just set it on fire.
Which is terrible for the environment.
This open burning releases massive amounts of carbon dioxide and black soot into the atmosphere, and it rapidly degrades the local soil quality.
Inua Mycotile intercepts that destructive cycle. They collect the wheat and rice straw and use it as a base substrate to grow mycelium.
Which are the mushroom roots, right?
Yeah, mycelium is the root-like, microscopic network of fungal threads that live underground. The mycelium acts as a living biological binder. It weaves itself through the waste straw, digesting parts of it, and aggressively locking the agricultural waste together into a dense, highly structured, porous panel.
Once the fungal network has fully colonized the straw, they press and heat cure the panels to stop the growth. This creates highly durable, lightweight building boards that can be used for ceilings, interior partitions, and doors.
I just love this thematic comparison. If metal organic frameworks are the microscopic synthetic sponges designed to save our atmosphere and our water supply, mycoboards are the macroscopic biological sponges designed to save our housing infrastructure.
It is a profound and highly relevant parallel. Both technologies rely entirely on a deep, fundamental understanding of structural networks and porous design. And the engineering properties of these biological microboards are astonishing.
What can they do?
They are naturally fire retardant, which is an absolutely critical safety metric for rural and rapidly upgrading housing developments. Because of their porous fungal network structure, they are highly acoustic, providing excellent sound insulation in densely populated areas.
And the innovation doesn't stop at just being a wall, just like how the chemists functionalized MOF 808 with amino acids to change its behavior. The engineers in Kenya are functionally modifying their biological mycoboards.
Yes.
They are infusing the panels with biochar made from natural, local, insect-repelling crops.
This is a brilliant public health intervention. By infusing the matrix with biochar, they turn the building material itself into a lifelong, passive mosquito repellent, actively fighting malaria transmission right inside the home without requiring residents to buy expensive chemical sprays.
Both MOFs and mycoboards represent the ultimate future of material science and logistics. Utilizing exactly what we already have, materials often completely dismissed as toxic waste or trash, to build highly structured networks, whether synthetic or biological, that fundamentally protect, filter, and sustain human health.
It's beautifully said.
Okay, let's take a breath and recap this incredible journey we've been on. We started at the atomic level, exploring the thermodynamic hurdles of reticular chemistry. We saw how early pioneers struggled with collapsing wet spaghetti until Omar Yagi engineered secondary building units, creating rigid molecular parking garages.
We examined how Yagi's background drove the invention of MOF 303, a material utilizing alternating hydrophilic and hydrophobic pockets to aggressively seed and release water, literally conjuring drinking water from dry desert air in minutes via rapid cycling.
We tackled the carbon capture paradox, learning how MOF 808 uses the very moisture that ruins older technologies to chemically transform CO2 into bicarbonate, completely bypassing the massive thermal energy penalties of traditional amine scrubbing.
We dove into the macro-engineering bottlenecks, highlighting the destructive nature of capillary forces and how supercritical carbon dioxide allows us to drain the solvent without crushing the structure.
And we discussed the massive scale-up potential of continuous flow synthesis, dropping manufacturing times from days to mere minutes.
We zoomed all the way out to visualize the critical logistics workforce of the 2030s, a global workforce that will rely on AI supercomputers to discover new materials, logistics experts to carefully transport sensitive molecular traps, and circular economy principles to build everything from synthetic MOFs out of acid mine drainage to biological mycoboards out of burning crop waste.
It represents a total global paradigm shift in how we fundamentally interact with the physical world around us.
It does. But before we finish, I want to leave everyone listening with a final, slightly provocative thought and unexplored implication of this reticular technology.
I'm all ears.
We have spent this entire time talking about massive frameworks capturing water and carbon dioxide.
Yeah.
But remember, the pores of these MOFs can be chemically tuned with absolute atomic precision to bind to incredibly specific, complex guest molecules.
Right. If you design the shape and the chemical coating of the trap correctly, you can theoretically catch anything that fits inside.
Imagine a future perhaps not that far off, given the pace of AI discovery, where the MOFs integrated into the HVA systems of your home, your office, or your local airport aren't just passively filtering out moisture or standard carbon emissions.
Okay.
Imagine if they act as silent ambient diagnostic tools.
What do you mean by diagnostic, like medical tools?
Consider the air we exhale. It is full of complex chemical signatures. Could a highly tuned, functionalized MOF silently capture and concentrate the very specific volatile organic compounds associated with the aerosolized shell of an airborne virus?
Oh, wow.
Or even more profoundly, could it trap and detect the subtle ambient chemical markers of early-stage human diseases exhaled by the occupants of a room?
That is a staggering thought. If the material in our vents could selectively trap the chemical signature of a disease before anyone even felt sick, we could essentially turn the very walls of our buildings into an ambient planetary immune system, just silently pulling life-saving data out of the seemingly empty space around us.
It entirely redefines what we consider empty space, doesn't it?
Yeah.
The space around us isn't empty. It's a dense matrix of information, and we are finally building the microscopic nets required to read it.
It really does completely change your perspective. The next time you look at a speck of dust or just stare into an empty room, remember there might be an entire football field of structural potential and the solutions to our greatest crises hiding right inside it. Thank you so much for joining us on this deep dive into the source material. We hope it sparks some new ideas for your own professional future. Stay intensely curious, keep questioning the invisible mechanics of the world around you, and we will catch you next time.